Okay, good morning everyone. So we will continue to talk about the p-n diode. So the main focus today will be focused on how we derive the current equation regarding for the p-n diode inside the p-n junction. So last time we have already mentioned that with considering this structure where we have the P and N in the left and then the right hand side, and then we already knew that in between we have this depression region. So last time we have already mentioned that right now we are interested in the carrier injected in the another side and become the excess minority carrier. So for example, we have this PN-XN, which is a hole injected from the P side and become the excess minority carrier in the N side. So which means this is a part that the hole injected from the P region reach to the N region and in the end become the excess minority carrier here. And also, this part we also have to consider the one that the N electron carrier will be injected from the N to the P side and become the excess minority carrier in the P region. So therefore we have this equation and this equation to describe the excess minority in this boundary condition. And also this difference will be our excess minority carrier from this depression region boundary between the equilibrium case, steady state case. So that would be the delta NP. So similarly, we can have this delta PN as well. So we will, based on this understanding, start to derive the equation. So this is just a very general minority carrier distribution equation that we consider the bipolar transport equation for excess minority carrier holes in the N region. And we all knew that this is related to the space and this is related to the time. And then the purpose is that we want to have this bipolar transport equation can describe the behavior of this excess carrier as function of the time and also the function of the space. And first of all, we will consider the electric field is 0 in both P and N regions, and therefore we can simplify this equation where our electric field is equal to 0 and our generation will be equal to 0 as well. And also we consider for the steady state, so the derivative of this excess carrier versus the time will be equal to 0 as well. And therefore this equation can be simplified as these two, which represented the space where x is larger than xn and x is smaller than xp. And this is a definition of a LP square, and then the definition for Ln square here. So with this considering the equation, so we will start to move on to try to adapt several boundary conditions to help us to solve this equation. So here is as we already have this equation, now we have to take into account the several different boundary conditions. First of all, with this equation, we can have the general solution from here. This is a general solution in the case where x larger than xn, which is this one, and also the x smaller than minus xp, which is this one. So this is the detail for this, how to have this general solution is not going to explain detail in this class, because of this is general engineering mathematics that you should already learn. So anyhow, the solution will be like in this way. Now the purpose is if we want to further to derive and solve this one, then we have to take into the several boundary conditions. So the first boundary condition will be, so we have the first boundary condition where we take into account the concentration, the minority concentration in this region. And also, similarly, we can have the second boundary condition where we consider this place. And also we have the steady state where the x approach to the positive. This is the x approach to the positive infinite. So we will have the BC3. And also the last one is a BC4. So basically, with the help of these 4 boundary conditions, we are able to solve the coefficient of the ABCD as shown in this general solution. To further understand this solution, so to further understand the solution for this minority carrier distribution, so we further try to analysis more details. So you will find out that with this it says a whole carrier concentration in the N region, so we can observe that there is exponential dependency here, and especially this is a decay exponentially. So the minority carrier concentration decay exponentially with the distance away from the junction to the thermal equilibrium values. And similarly, we can have another exponential decay from the excess electrons in the P region. Therefore, if you try to plot this distribution along the X space, so first of all, we'll have in the middle of the depletion region, and then we have the minus XP and positive XN here. So this is our boundary of our depletion width here. And then for the equilibrium, we all knew that the left hand side is we have the NP0. And the right hand side we have a PN0. So left hand side we have NP0, and then right hand side we have PN0. And we knew in this location we have the carrier distribution, especially the minority carrier distribution, we can express as a NPX, because this is minority carrier distribution is the X space dependent. And also we have this one where we have the PNX. So from the equation here tell us that actually this excess minority carrier distribution has an exponential decay, and therefore we can expect the distribution curve will have this profile, where this is our excess minority carrier in the P region, and we have this exponential decay. So again, the physics in the beginning probably is a little bit complicated, and then of course if you look at for the detail for the equation derived, although we don't go very detailed, but the equation sometimes looks a little bit scary as well, because we consider the full equation for the n bipolar transport. But now in the end, the answer is very simple. So we can expect that once we have excess carriers in this boundary, and then we'll have the gradually exponential decay in the end to reach to the thermal equilibrium value. So especially the exponential decay is one of the most popular equations that we will see in the physics, that we use a lot of exponential decay function that to describe a lot of phenomena. So similarly, if you look at the right hand side, consider for the Pnx, then still we have this exponential decay, and this is related to our excess minority carrier in the N region. So now we understand that once we consider this, this is our p-n junction. So once we have electrons inject from the right to the left, and once reach this region, and this electron will become the excess minority carrier, and afterwards this excess minority carrier will have the exponential decrease behavior in the end to reach to the thermal equilibrium value. And similarly, the holes will be injected to the right hand side, and once the holes arrive here, become once the holes become here, then we have this excess hole carriers in the N region, and then we'll start to exhibit as an exponential decreasing until to reach to the thermal equilibrium conditions. So, because now we have the excess, electrons in the neutral P region, which is this one. And also we have excess, sorry, this should be this one. Excess electron in the neutral P region, which is this one. And we also have excess holes in the neutral N region, which is this one. Therefore, we already mentioned that when we take into account of the excess carriers, then actually we cannot consider the pure Fermi level anymore. So we have to consider the quasi-Fermi level. So now we have to apply again the quasi-Fermi level into these two regions. So that's why in the previous lecture, when we talk about the non-equilibrium excess carrier, we introduced the concept of quasi-Fermi energy, because now we have to use this concept, and therefore the equation here on the P is equal to the P0 plus the excess hole which will be equal to Ni exponential EFI minus EFP over KT. And now the EFP here we consider as a quasi-Fermi energy, quasi-Fermi level. And similarly, we can have the N, we can have the N is equal to N0 plus delta N is equal to Ni exponential EFN minus EFI over KT, where EFN is a quasi-Fermi energy as well. So these two are quasi-Fermi level. So that's the purpose why in the previous chapter we introduced the concept of quasi-Fermi energy, because now in reality when we consider a real device, indeed that we will face the issue that they will have the excess carriers in the certain region, and therefore we cannot use the pure Fermi energy concept anymore. We have to introduce this quasi-Fermi energy here. And the carrier concentration are exponential function of the distance. Therefore, the quasi-Fermi level will become the linear functions of the distance in the neutral P and N region. So what does this mean? This means that if now we consider as a band diagram, where first of all this is our depression region, and we have in the left hand side is P, and in the right hand side is N region. So first of all we consider a conduction band like this one. This is our EC EV, and also in the right hand side we have the EC EV here. EC and EV here. So we all knew that because this is in the one system, so therefore the band diagram must be continuous. So therefore there will be a certain band bending in this depression region. And also if you consider for EFI, which is in the roughly in the middle between EC and EV, so that's EFI. So as usual we have this band bending in this depression width. But now we have to take into account of the quasi-Fermi energy. So in the case of the N region, so we have the quasi-Fermi energy close to the conduction band because this is a N-type region. So this is EFN. And also the left-hand side, we have this one. So this is a EFP as well. But now the question is that how this EFN inside the depression region and also inside another opposite region. So and then because of this will only influence when we consider the EFN is we consider excess carriers. So in this middle of this region is mainly the carrier is mainly transported by the electric field. So because the electric field is the same, so we can consider the EFN and EFP are the same inside the depletion width. But now, because of we already knew that in previous derived that we have shown that the carrier concentration are exponential. But once we consider exponential inside the Venn diagram, if you look at the Poisson equation, then you will understand this will become the linear function. Decrease here. So this will become the linear function decrease in the neutral N and P region. This is because our carrier concentration is exponentially decreased. And if you plot in the Venn diagram, that will become as a linear function. So this linear function actually indicates that our carrier concentration has exponential decay. So this is something that you will see that the Fermi energy, quasi-Fermi energy in the original P and N region, and also the quasi-Fermi energy in the region that where they become the excess minority carriers. So furthermore, still have to figure out that our purpose is to have the current equation. So then we still have to do the state by state in the end to derive for the current equation. And at the space charge region, x equal to Sn, and also we consider the case of under the low level injection, and therefore in the case of x equal to Sn, which will be this one, this is x equal to Sn, and now our carrier concentration product where our N0, so that's a majority carrier concentration in the N region, so this is N0 times Pnxn. So now we are trying to calculate the carriers for the Pnxn times this one together, and this can be equal to N0 Pn0 exponential VA over VT. And also, we have already knew that this term, this N0, that means the thermal equilibrium electron, right? And then the Pn0, that means this is thermal equilibrium hole. So once we have the N times P in the thermal equilibrium, so this will be equal to Ni squared. So now we can reform our equation, become exponential VA over VT. So that's a equation. Now we play the certain trick here because we want to have the term of Ni squared inside this formula. So now we finally have back to something that we are familiar with, which is the intrinsic carrier concentration. So the same when we consider Therefore, the N0P, now we can have this one. This is N0P is equal to Ni squared exponential Efn EFP over KT. So the difference in quasi-Fermi level is related to the applied bias VA here. And also the difference between EFN and EFP is nearly constant through the depletion region. So this is a sentence to describe that it's almost constant in the depletion region. And then the difference between this one and this one is mainly due to our applied bias. So now, to move on for the further consideration with current, the total current in the junction is the sum of the individual electron and Hall current that are constant through inside the depletion region. So in the end, the trick is that how do we further derive the current equation? We consider that the total current here, first of all, the total current is sum of the Hall and electron current. And secondly, that inside this depletion region, actually the current are almost constant because of our Fermi energy is constant as well. So now we can consider the sum of this one plus this one, which will be equal to the total current of this one. And because of this is inside the same system, so the current here will be exactly the same like the current here and the current here as well. So that's a trick that in the end how we further derive the current here. So since the electron hole current are continuous functions through the p-n junction, so the total p-n junction current will be the minority carrier hole current plus the minority carrier electron diffusion current. So now, to further derive the current, we try to consider this part, this plus this one. This plus this one. And then in the end, we should be able to get the total current. The consideration or reasoning for trying to derive the p-n junction sometimes not that very intuitive, because there's a lot of physics and also lots of mathematical trees behind. But in the end, it's just want to let you know that why we spend the time to understand the current at this point and this point. The purpose that we spend the time to understand the current here, because in the end we want to leverage these two current, and then the summation of these two parts will be equal to the total current inside the p-n junction. So now, and especially now, what we are actually interested in is the diffusion current here. So we back to our typical diffusion equation. Now we have to consider the minority carrier diffusion current. Which we have this equation, then will be also can be reformed as shown in here. And because now we consider uniform dope, so thermal equilibrium carrier concentration is constant. So the whole current density for this forward bias, now we consider the forward bias condition in the x direction can be in the end considered as shown here. And also the same, we consider this equation, and then where we already have this formula, then in the end, our Jn minus Xn is equal to exponential VA over KT minus 1. So that's a whole current and with electron current. So the total current density, the total current density current density in the PN junction, which is equal to this plus this, and in the end will become this one. And normally this is a constant parameter that is independent of the bias. So therefore we define this one as a Js, where Js is equal to and then in the end, the most important part is that our current equation J proportional to our exponential EVA over KT minus 1. That means our current here is related to our bias in our PN junction. So therefore, if you try to plot the IV characteristic, where this is a current versus our bias here, then we'll get this exponential increase of our current under the forward bias condition of in the one PN junction. By the way, that I saw that many of you actually is no more than 99%. I don't know why still will someone didn't. There's you know, for last week we have a meeting exam. I think there's a one additional 5-point bonus for everyone. As long as you write anything, you will get a point. But I didn't know that why still somebody missed that question. So that's very pity for everyone, because if you don't write anything, I cannot give you the score. But whatever you write, even just write the good, you at least get the 5 points. And I just quickly go through the overall every suggestion from everyone. I think more than 98% of you are very satisfied that in this class we won't spend too much time in the equation derived. We focus on more physics understanding, and also I think most of you are very I would say very satisfied that we try to link the result with transistor level in the MOSFET or diode even in the beginning. I just want to comment that there are still few of you suggest that we should spend more time to further derive the equation in very detail. But I would say it is not possible in this class, because I think the purpose for this class is not like the every equation we have derived here. It just the main purpose is just for the physics-based understanding. It's not like that you have to be very familiar with all the detail. For example, how to solve this equation and what would be exactly the calculation inside. If you are interested in, I think there's a textbook. Okay, so you can look at the textbook. You should be able to find yourself. If you don't understand, you can still talk to me. But I would say that due to the time limitation, I think it's very difficult that we try to explain all the equation in detail. And especially, I would say that this equation in the future for your job, for your future research, to be honest, you don't remember all this equation, because of all this equation already basically that written in the software or in the simulation tool, and you can easily find the internet. But the most important is the physics, because physics is more intuitive. That's more help you to further analyze the semiconductor, and rather than that just to put too many efforts that try to derive the equation in the detail. So that's my brief reply. But still, I think more than 98% are still try to. We hope that we put less effort in the equation, more effort in the physics. I think I will still try to make this class in this way. And also, I remember there's one very impressive. There's one comment very impression that some of you actually try to in the beginning of this semester, because as you know that in NYC we have the multiple professors that offer semiconductor physics device in this semester, no matter in this semester or last semester. And then I think some of you make the comment that in the end why you choose this class is because of you found this is more physics oriented, and other professor probably more focused on mathematics. And then sometimes if you dive into too deep in the mathematics, you get confused about why we have to learn. But so that's why I will put the course style in this way. So probably I will still try to follow the 98% of your opinion and only 2% with students. So if you still got a problem to understand the equation, you want to talk to me, of course you are feel free to come to talk to me. Otherwise, you can look at the textbook. I would say that everything in detail. Whatever I didn't mention, whatever I miss, or whatever I make the mistake, you can all find the details in the textbook. The textbook is a Bible that you should read it time to time. Okay. So now, furthermore, so we will start to try to complete the full picture for our IV characteristic. So we already have the IV characteristic that we have already derived, where I have the current versus voltage, and in this case we have this one exponential increase, where the J is equal to Js exponential EVA over KT minus 1. And also here we have the derive the term what we call the Js, and the Js is sometimes we call as a reverse saturation current density. So that means the Js is a current, is a constant current when we apply the reverse bias, and where this is minus Js. So ideally, under the reverse bias condition, we will only have this small reverse saturation current. But unfortunately, once we go very high, we start to face the issue of the breakdown. So that's a full picture for our ideal PN junction, which is a PN diode. So then, this equation is a one that you probably will see in the very often, and because this is a one that if you have already followed the electronics, so when we are learning from the electronics inside, they always use this one to represent as a diode current, so which is expressed like this one. And then in most of the very genetic diode model, PN junction model, we always use this equation. So then now we start to move for the some of the additional small concept. It's not still very important because it's something that you will still face, that if you are in the field that work a lot in the diode. So here is a summary. So summary of the physics that in here we consider that we have the forward bias voltage applied in the PN junction, and then the forward bias voltage will lower the potential barrier, so the electron and holes are injected across the space charge region, and the injected carriers become minority carrier, which then diffuse from the junction and then recombine with the majority carriers here. And the minority carrier diffusion current decays exponentially in each region, and the total current is through the PN junction is constant. So therefore, we can leverage these two minority carrier and combine together will become the total current here. So here is a summary of what we have been explained before. If you can understand these 4 bullet points, what does this text mean? If you can understand the meaning of this text, that means that you can understand what we have been discussed in previous in the previous page here. So that's a main key summary of physics. But with under this understanding of this physics, you need to go through to check the page we have to talk about. So still, there's one more thing that might be happening is that we have to consider the generation recombination as well, and also there's an issue related to the high level current injection. So we already knew this from the previous SRH series that this is a typical equation when we consider the recombination. And once we apply the reverse bias here, actually the reverse bias, we need to take into account of this generation, because of the under reverse bias, there's a chance to generate the electron hole pairs in the space charge region. So this can be the multiple factor. One is due to the you have the additional carrier being injected, or because it start to induce the impersonalization. So in anyhow, under reverse bias, we need to take into account this generation current. So as electron and holes are generated under reverse bias, they are swept out of the space charge region by the electric field, and the flow of the charge is in the direction of the reverse bias current. And this reverse bias generation current is in addition to the ideal reverse bias saturation current. So what does this mean? This means that under the reverse bias, we have to take into account there is an additional generation current. In previous graph, we have already mentioned that the typical IV characteristic, which is this one, we have the forward and then reverse. In the ideal case, we have a very small reverse saturation current, which is Js. But now, because of due to this additional electron and holes are being generated, where we have this generation current. So in most of the case, you will start to see under the reverse bias, our current is getting larger and larger. This is due to the generation of the electron holes. So that's the curve. In reality, you will see. You will never see the PN junction, PN diodes that always exhibit a small saturation current under reverse bias. This is not reality. In reality, you always see the current is gradual increase, as shown here. And also, one additional concept, this is a reverse bias generation current. But however, under the forward bias, we also have to consider that there's a chance of the recombination. So under the forward bias, the electron and holes are injected across the space charge region. So we have the holes inject to the right. We have electrons inject to the left here. And then you can expect that once electron holes meet with each other, there's a chance that the electron hole can be recombined. So therefore, there could be a recombination happen. So some excess carriers in the space charge region. So we have the holes being injected to the right, electron being injected to the left, and then we have the excess carrier in this space charge region, and this excess carrier will recombine inside the space charge region, and therefore this will cause a forward bias recombination current. And also, if you try to look at the recombination rate versus the distance, so then you will find out that in the middle we have very high recombination rate, which is very straightforward. So once you have an additional electron and holes meet in somewhere, especially in the middle, and for sure that we can expect that these additional electron hole can be possible recombine with each other, and therefore there's a generation of a recombination current here. So in the end, this will also influence our total forward bias current. So the total forward bias current will be the sum of the recombination and then also the ideal diffusion current, and therefore your total current will be equal to recombination plus the original minority diffusion current. So in the end, we take into account all these factors, then we can understand actually the current factor is not only dominated by the diffusion current, what we talk about, there's a factor related to the recombination current, which is shown here. So this recombination current has a slope equal to 1/2 here. And then the ideal diffusion current has a slope equal to 1. And where the n is, we actually, in reality, that sometimes that we cannot always get the slope equal to 1. So we put as a n inside this current equation and become as a one tuning factor, one tuning parameter, and this n is called as a ideally factor here. So this gives us a way to evaluate that how our forward current can be ideal or not ideal based on the how large of n can be. So if our n is approach to the 1, so that means that our IV curve is a pure diffusion dominant, which is good. That's a very ideal. But if we have some other factor like n equals to 2, that means there are some mechanism dominating in this forward current here. So in the end, the total current is become the combination of these two. So this is a total current, and then we can see the two slope. One is under median operating bias, and one is under the low bias. And under low bias, this is a recombination. Under low injection. And another factors we have to consider is that it is possible that we will face a high level injection under the PN junction. So if we consider that a typical PN junction as shown here, so, and then once we apply the forward bias, where we have a VA, and now I think everyone can, even we don't talk about equation, we don't talk about too details in the band diagram, so everyone can expect that with this operation, we have a hole inject to the right hand side, so that's a hole injection, and we have the electrons inject to the left hand side, which is electron injection. So now it can be the issue. In previous discussion, we assume that the low injection, which means that this is the ideal case. But there could be at a certain moment that if our injected carriers larger than our background doping, so that means our background doping in this region is N, but now we have the very high hole concentration being injected. So this hole is higher than this N. So that's the case we call the high level injection. So now we have to look at that what will be the issue that once we have a high level injection. So as the forward bias voltage increase, the excess carrier concentration increase and may become comparable or even greater than the majority carrier concentration. So which means in this case is mean, for example, we consider the doping here is let's say this is N0, and now we have the injection hole, which is a Pn. So now this is a case where Pn larger than N0, or this is a P0 and we have the NP. So this is a case where NP larger than P0. So now this is a case that we call as a high level injection. So now we just put the equation where we already shown before, but now we have to take into account of the excess carrier. So N is become the N0 plus delta N. P is a P0 delta N. And because of now the delta and delta P, delta N and delta P is much larger. So therefore delta N is larger than N0 and delta P is larger than P0 as well. So therefore this equation will become, this can be ignored, this can be ignored, and then this will become this one. And now we assume our additional electron and holes are equal. So therefore this is equal to this one, will become Ni squared exponential Va over 2 Vt, which the main difference is now we have the factor 2 in the bottom. So that means our current equation should be proportional to the exponential Va over 2 Vt. So what does this mean? This means if you try to plot the current versus the bias, which for example we talk about the log I versus the Va. So we already knew in the typical operation bias we have the idea current where we have ideally factor n equal to 1. And in the previous page, we talk about under the low bias. Under the low bias, we have the recombination. So the recombination will also give us an ideal factor equal to 2, which make our slope become smaller. And but now, under the high level injection, what would be the condition under the high level injection that is actually happen when we give the large bias? So this will happen once our bias is larger enough. So because once we increase the bias, and we actually inject more and more the holes, and then the electron will be increased to inject to the other side. So then in this case, exponential VA over 2VT, right? So this is because of these two is due to the high level injection, which is here. So this actually becomes the limitation. This will limit the performance under high current operation. So that's another issue for our PN junction. It's not only under the low bias we suffering for recombination, but under the enough high bias we also suffering for this high level injection. So that will limit our performance under the high current operations. Okay, so we will take a break and then come back in the 10 minutes. Okay, so now we will start to move to the next chapter. So we are getting close to the transistor. So now we finish the PN junction, and then before we move to the MOSFET, and then there will be another crucial concept we have learned first, which is related to the metal and semiconductor. So let's look at the full picture for the one transistor, especially in the case of MOSFET. So as we already knew that inside the MOSFET we have the substrate, we have the source, drain, and then on top of the source drain we have the dielectric in the channel, and on top of the dielectric we have the certain metal, and we have a source and drain and gate here, and this is our dielectric. But the one thing is that we very often not to plot just for the convenience, but we should actually always include is that with each terminal we should consider there is a metal, which means that in reality the device should not be as simple like this one, should have the metal in any region where we want to give the bias, we want to sense the current. So this is our metal. And the purpose to metal is that with this metal, finally we can apply our bias, we can sense our current. And also this is a metal that usually we try to put as a 0 volt, as a grounding. And that's why this lead to the issue that we also need to understand what happens in between the metal and semiconductor, which is this region. In this region, we consider this is a metal semiconductor junction. And then in the beginning of the introduction in this class, we already mentioned that when we talk about the metal semiconductor junction, there are mainly two types. As far as know, it's almost like a two type. Probably there will be the third one, but in most of the case, we only consider these two types. Which one is a Schottky junction? And another one is ohmic. And in this chapter, we will discuss what is the condition that will cause a Schottky junction, and what would be the condition cause the ohmic junction. And the main difference between the Schottky and the ohmic, for sure, that's if you look at the IV characteristic, where the current versus the voltage, the ohmic junction, why we call it ohmic junction, because it follows the ohmic laws. So the ohmic law is just basically that considers the resistance equal to the current divided by the voltage. So therefore, we consider the ohmic junction. So usually we should have the very good, very straight IV characteristic that will cross over the 0 point here. So this is a typical characteristic for the ohmic junction. But however, we consider the Schottky junction. The Schottky junction has a similar characteristic like our PN diode, where in the beginning we have the one turn on voltage that we usually call as a VF, and then the current will start to increase. So we have this is one that we call it Schottky junction. And also under the reverse bias, in the beginning, we should have very low reverse bias current, but in the end, we will still face the issue of the breakdown as well. So these are the two typical electrical characteristics for the Schottky junction and then the ohmic junction. So in this chapter, we were going to discuss why, what would be the physics behind, and what would be the condition that can cause these two different kind of a junction. Okay, so then we still have to back to the fundamental part is related to our band diagram. So as already mentioned that now, since we start to introduce a concept of band diagram, then the band diagram will be a basic tool allow us to analyze all kind of the physics phenomenon inside the semiconductor device. So right now we consider a band diagram, which first of all, we have the metal in the left hand side. And now we consider the p-type semiconductor in the right hand side. And this is a condition that we have not put the metal on top of the semiconductor yet. We just have the two pieces of material that being separate with each other. So with the right hand side, the p-type semiconductor, I think everyone knew that the band diagram should be for sure that we have the EC, we have the EV, and because of this is a p-type, so that means our EF close to our valence band, and also we have the EFI, which is intrinsic Fermi energy here, and this is a the material for p-type semiconductor. And then to further have the reference energy level that we can define. So usually we will define a region, which is this one. This is a one that our reference energy level, and sometimes we call as a vacuum level here. So now we can define the difference between these two. It's what we call the electron affinity. So this is electron affinity. And also, we can define this is phi s, which is a semiconductor work function. And this is some definition in the semiconductor side, but now we also have to take into account the definition in the metal side. In the metal, we don't have the valence band and we don't have the conduction band, valence band. We only have the EF. This is a metal Fermi energy. And the difference between the metal Fermi energy versus the vacuum level, this is our vacuum level, which is E phi m. And this is a metal work function. So this the happening when we consider our metal Wolf function is larger than our semiconductor Wolf function, which means phi n is larger than phi s. And this is a case that these two materials that haven't been connected with each other, just a little bit separate from the metal side and semiconductor side. And for sure, the things we are interested in is that if we try to put these together on top of semiconductor, and what would be the things happen? The first things will be happening is that once this material connected with this one, and these two will become the one system, and once become the one system, and therefore Fermi level become constant through the system in the thermal equilibrium. So that means right now we only have a one Fermi level, because Fermi level it must be the constant, because this is a condition that we didn't provide any bias. So that means now this will become still, we have a left hand side, a right hand side is a p type, where we have the EC EV here. But now this is a little bit changed from for the figure illustration purpose. So the right hand side, what we discuss here is N-type semiconductor. So in the case of an N-type semiconductor, we have EF is close to our conduction band. And then we still have the EFI here. But now, because of the metal Wolf function must be constant and through all the system, so the metal Wolf function have to align with this one as well. So this will become our EF in the metal side. And now we can foresee they will start to have the band bending. Where this will become in this way. And this band bending also suggests this is a depression region. And why we have a depression region? And actually we can borrow the understanding from the PN junction as well. So in the case of PN junction, now we consider this is a piece of the semiconductor where this is N-type. And then now we put the metal on top of this. So we have a metal here. So this is our metal. So with this depression region band bending here suggests that inside this region we have a depression as well. So that means we will have the depression region happen. And then with understanding coming from the PN junction, but the same concept can be applied here. So we can expect that there will be the positive charge in the depression region of the N side. here. So this in the end will form this one, so which will be very consistent related to what we learned from the p-n junction as well. So then we have several terms can be defined. One is a built-in voltage. This is a VBI. And also we have this one, which is a 5B, the barrier high. So we will make some more definition, clearly definition later. But the thing is that once metal connected with N-type semiconductor, positive charge donors often remain in the semiconductor and create a space charge region. So this part is this one. So the concept is exactly same like a p-n junction, but now we just replace the P as a metal. So this graph is shown again in the bottom, and now we can define the 5B0, the 5B here, which is our metal work function minus the electron affinity, and also the VBI is equal to the 5B minus the phi n. So with a different material, we have a different electron affinity. So as you can see here, silicon has an electron affinity of 4.01, and with a different metal, we have a different work function. So this is very often used. For example, aluminum, gold, nickel, palladium, titanium. So these are the metals that we very often use in the semiconductor. So after we apply the positive bias to the semiconductor, with respect to the metal, the semiconductor to metal barrier height increase, while 5B0 remain constant in the ideal case. Then these conditions that we call as a reverse bias here. So this is a condition that once we have this one, so we have the EC, EV, and this is considered for the N-type semiconductor. But now because we apply the reverse bias, so the difference between the EF in the metal side and semiconductor side will not the constant. So therefore, the EF here is become, this is an EF in the metal side, and the difference between these two is our reverse bias, VR. But still, this is the same material that have the same barrier height. So we still have the same barrier height. Like the previous page where we have a Q5B. And now we will, in this case, we will form the Venn diagram. Where something like this one. So we have the band diagram will be exhibit like this here, and then we will have the building voltage where VBI plus VR. So this is exactly the same analysis, just like our PN junction, but now we just replace the P as a metal here. So the positive voltage is applied to the metal with respect to semiconductor, and now the metal semiconductor barrier. This is a case of reverse bias. But now if we apply the metal, to apply to a metal, then the metal semicon barrier VBI is reduced. So this is a case of the forward bias. So in the case of forward bias, the same Venn diagram we can plot so we have a EC, EV, and EF. But now, because we apply the forward bias, and so the positive bias in the metal suggests that our metal wall function is lowering, as shown in here. So the difference between these two is our forward bias here. And because of this reduced, so now our barrier high is reduced as well. So the electron can move easily from the semiconductor to the metal since the barrier is reduced. And then the barrier here is the same. So this is very similar to the previous analysis in the PN junction. As I say, we just replace P as a metal here. So now the next step is that with the understanding of the Venn diagram, for sure that to further understand the charge, potential, electric field, we have to use the same way to analyze the charge distribution, and then to further calculate electric field and then the potential in the end. So determine the electrostatic property of the junction in the same way as we do for the PN junction. So now we apply the Poisson equation where our dE over dx is equal to rho x, which is the charge distribution in the x direction, over our dielectric constant. So this is the same that where we already mentioned before. And then we just apply this to the first integration, then we can have this electric field. and then the electric field is 0 in the space charge region, and therefore we can obtain the constant C1, and then we can have the electric field assuming this formula. So we can further calculate the space charge width with consider the junction like here. We have the P, then we put the metal, and we already knew that between this metal and semiconductor, they will have the formation of the depletion width, which is W here. So the space charge region width might be calculated as we do for the PN junction, and then the equation is shown here. And one thing I want to mention that actually this depletion width will be very similar to what we already discussed before, that we consider the one-sided PN junction. So now we can see this W, and then this will be very similar to the case in previous. We have already mentioned there's one special case that we have the P here, but on the other hand we have the N++. So in that case, the depletion width, which is W, is equal to WP. And this will be exactly the same like this one. So depletion width W is equal to WT, because we can consider the N++, which is a heavily doped, is the same, almost the same characteristic like the metal, because once we dope the semiconductor in the very high concentration, then you get the characteristic with a very low contact resistance, low resistance. So that's exactly like the metal. So that's why in the previous chapter we have particularly mentioned this one-side PN, because in the end we will use the same concept in here to explain the depletion width in the Schottky junction. I just want to make a reminder that the equation we are considered here is metal on top of the N type of semiconductor. So this is a N-type semiconductor that we consider as a metal here. So that's why we have the ND and also XN here. So we have an ND. So this is equal. So this is so it's different like what we say here, but the idea is the same. But now this equation is considered that we have a metal on top of N-type semiconductor, which is this one. This is a metal on top of N-type semiconductor. And then one more thing is that also from the suggestion that some of you actually request that we should do more like the demonstrate how to use the equation to solve the questions. Of course, this is not my original purpose. Is that I still hope this class will be focused on the physics-based understanding rather than use the equation, because you guys have been in the college since junior high, senior high, university. You have been used equation, try to do the calculation many times, and then you, of course, I can understand that everyone is get used to in the class in the way that the professor or the teacher will try to solve the question step by step, that teach you how to use the equation. But I still want to mention that the equation is not the main point. The purpose for the equation, for example, in my class, the purpose equation just to have the exam, to have the homework. It's not like I ask everyone to really try to solve everything very efficient to memorize this equation. But for the midterm, I have no choice, because otherwise there's no way to do the very fair grading, because if I don't assign the equation-based question, then there's no way to do the fair grading. So we have to still follow the conventional way for the homework for the midterm. But the final is fine that it's open book, so you won't see that you even didn't have to just try to memorize any equation, because in any way you will find it from your textbook or whatever. So, but still, every year I got some requests that some of you always request that we should try to teach some equations, how to use the equation. But the purpose is that usually I try to doing the way that the homework is a different style than my teaching, and in that case you can have the chance to train yourself in another way. If I teach the same like homework, then what's the purpose for homework? Because everyone is learning the same solving style. But as being the graduate student, as being the engineer, for me the calculation sometimes not that the key point. The key point is still mainly like try to understand the physics, because in real world you very less chance to use this equation. But anyhow, as request, so time to time, if you gather some time, I will be still love to try to do some calculation for everyone. So this is an example that just a little bit guidance that why we use this learn from this equation, how we apply this equation. So the question is that determine the theoretical barrier height and built-in potential barrier, and then the maximum electric field in the metal semiconductor diode for the zero applied bias, and consider the contact between the tungsten silicon dope at a certain doping concentration and also at the one temperature. So in this case, first of all, we have the consideration that for the metal work function for tungsten, so that's a phi m tungsten, which is equal to 4.55 volt, and then we have the electron affinity 4.01 volt. By the way, just want to mention that if I try to lecture more questions in the class, in the end, that will be situation that your exam will be more difficult. Because easy one, I will lecture in the class. Then I have to come up with more difficult question for you. So try to get used to, we are not like a high school or typical university like under class. We are not teaching everyone to solve the question. We are not like the professor or teacher in the crane school to help you to get a high score. Okay, so but that's always a pros and cons. So you have to understand that if I teach more in this style, then the exam will become more difficult because I have to come out with the question that I never teach in the class. Yeah. Okay. So this is a basic parameter, and then from previous equation we already know that the barrier height for phi B0, barrier height is equal to phi m minus the electron affinity, so which is this one. That will be equal to 0.54. And then we also know that the phi n which is equal to kT over E natural log NC over ND here. So that's in the end is 0.0259 natural log NC, which is equal to 2.8 times 10 to 19, and over 10 to 16, which is ND. Then that will become the 0.2. So now our goal is try to calculate the VBI is equal to phi B0 minus phi n is equal to 0.54 volt minus 0.206 volt. It becomes the 0. So that will be the first answer, the theoretical building, the theoretical barrier height here. And then the second one is space charge width at the zero bias. So as you know that we have the equation xn equal to this one, which is a 2 VIS X zone VBI over END. And in the end, that's equal to 0.208 times 10 to minus 4 cm. And then now we have a maximum electric field. It's equal to E max ND XN X zone S, which is equal to 3.21 times 10 to 4 voltage per centimeter. So that's a maximum electric field. So then you can see that this is just a very basic calculation. It's just we try to put the equation we knew before. We just put in and then just try to calculate some number. But usually, if we just learn how to calculation, actually we don't get so much sense, because this is just a bunch of the number like generate out from the equation. So I want to still stress that the physics inside the Venn diagram is much more important than this calculation. But for the exam homework, there's nothing we can do, because otherwise it's very difficult to do. If our question is very open to ask you to draw the Venn diagram, to have very like the open style question rather than the calculation, then we will got the issue for to have a fair grading, because my opinion might not be the same as your opinions. Okay, so but one thing want to be interesting to know is that with this calculation, there's still one particular interesting concept that we should know, is that we consider the case where this kind of the Schottky metal, this kind of metal semiconductor junction, that we have the ND, in this case ND 10 to 16, and we put the metal here. So now we already knew that with this consideration, we will get some certain depreciation width. So with this depreciation width, then we can have the maximum electric field. So maximum electric field, that means that this depreciation width in the end can sustain how large the breakdown voltage can be, because the breakdown voltage is already related to the maximum electric field. So right now we have this concentration can reach this maximum electric field, and then after this maximum electric field, we will start to have a breakdown characteristic. So this is a condition when E is larger than E max. So we can start to see the breakdown happen. But for me, the most important concept from this calculation or this analysis is tell us that once if you change the doping concentration, you increase your doping concentration here. You increase the doping concentration in this region, and then actually your depletion width will decrease. So then you will have the second depletion width. Your depletion width will decrease, and once your depletion width decrease, so likely you will see your breakdown voltage will change as well. So this is more important to understand the meaning of the Emax. So the Emax means that this is the maximum electric field for this inside this depletion region. So as long as our applied electric field is larger than Emax, then we start to face the breakdown, electrical breakdown. And then also Emax is related to our depletion width. So then we change the depletion width, in the end will influence our breakdown voltage. Okay, so still the same, we can also try to estimate the junction capacitance, which we will do the same for PN junction. So then we can have this junction capacitance formula, and then we plot 1 over C square is equal to this one. So we can still consider to fabricate the metal and then the semiconductor as capacitance. And in this case, if we try to have the structure P sub metal, then we measure the capacitance and plot us like this way. And then we can extract NA and VBI. We can obtain the built-in potential barrier VBI, and the slope we can get the doping concentration. So that's the same purpose if we do the capacitance in the PN junction, we can also calculate the doping concentration as well. And then another non-ideal effects we have to consider is what we call the Schottky barrier lowering. So the Schottky barrier lowering is mainly due to the very fundamental physics phenomenon that we call the image force. So image force will induce the barrier lowering effect. So imagine you have this is metal semiconductor junction, and then in the left hand side you have a metal, in the right hand side you have a junction. And then if you have the one charge formation in the metal, and then we'll have the image, if there's a one charge formation inside the junction, and because of this is metal, so we will create the image charge here. Image charge here, and because of this image charge, so we can start to have this image force. So this graph should be something that you are familiar with if you learn the electromagnetics. So in the first few chapters of the electromagnetic, actually we are consider that we have two charges separate the one certain distance, and how do we calculate the force. So this is the same concept here. So we have a distance, right, is this one, x, so will be the same distance to generate the image charge here. So an electron in the dielectric material at the distance x from the metal will create the electric field. The electric field can be determined by adding the image charge E inside the metal located at the same distance of the x from the interface. And with considering this image force, so we can borrow the equation we learned from the electromagnetics here. Then, in the end, we can have the calculation that this image force will cause, this image charge will cause this kind of the influence of our potential. And the most important is next one is, once we consider this Schottky barrier lowering effect, in the end we have this barrier decrease with a number of the delta phi b. Why is a delta phi b? Because of this one is negative. So that's why in the end there's a barrier decrease here. So the barrier decrease will cause the certain issue. First of all, let's look at this equation that this barrier decrease delta phi is equal to over 4 pi epsilon s. So this suggests that as long as our electric field is larger, is increased, and then our barrier decrease is increased as well. So the electric field increase, then our delta phi is also increased. And then in the end, our new delta phi, our new barrier height, Q phi b prime, is equal to original Q phi b minus delta phi. And now this increase, so this will decrease. So what will be this impact on our electrical result? This is most important than the equation. So if you look at the typical IV for Schottky diode, we already knew that in the beginning we should have a small reverse saturation reverse current, and after reaching the maximum electric field, and that will cause the breakdown. But we consider this barrier lowering effect, we can start to see even at a lower bias, because of a increase of voltage, then will cause a barrier height is decreasing. So barrier height decreasing, that means the current is already increased at this low voltage part. In the end, this will cause our breakdown voltage decrease as well. So now we can see this is exactly the same phenomenon illustrated here. So with no barrier lowering, we have a very low current. With a barrier lowering effect, we have a high current here. So So because of the reverse Lie current now is related to the phi b minus delta phi bm. And also similarly, this is coming from another textbook, and they also mentioned that this is, if we consider the Barry-Lowing effect and also the average breakdown. So that is actually more important for this, the implication for this physics phenomenon. And similarly, just like the MOSFET, in the beginning when we talk about MOSFET, we also talk about there's an issue for the interface state. But also in the Schottky-Barrett diode, we also face the same issue that we call as the interface state. So the interface state, if we look at the MOSFET, we have the source and drain, and then we have the dielectric, and we already knew that because of the interface state can happen in this region, it's because we have a certain break the bonding between the silicon and silicon, because this one is a terminated silicon interface. So we have this very nice silicon bonding with other neighboring silicon atoms. So we have this one, but unfortunately we must terminate our silicon in somewhere because we have to stop there and put another different material. So this termination in this region will create lots of allowed energy state in the forbidden band gap. This creates a lot of allowed energy state in the forbidden band gap, right? This is what we already mentioned, that ideally, why we call it forbidden, because the forbidden means that ideally there should be no any energy level state inside this band gap, which is EC, between the EC and EV. And because of this termination, so that's create a lot of allowed energy state, and then this is become the interface state, because this state is existed in the interface region. So similarly, for the Schottky-Barrett diode, we also have the same issue for the interface state. The Barrett height of the metal semiconductor junction is determined by both the metal work function, but also the semiconductor surface. Or interface state, which is here. So in the previous, when we talk about the MOSFET, the interface state is due to some of the trapping, detrapping that we will talk about later. But in here, for the Schottky barrier die, when we talk about interface states, because in the end, it will influence our metal work function. And then it also will influence our barrier height. So assume that all states below the surface potential of phi 0 are donor state. Which will be neutralized if the state contains electron and partly charged if the state does not contain electron. So that's a definition for the donor state. And then we assume that all states above phi 0 are acceptor state. So again, this is a definition of the acceptor state, which we already mentioned. Then we will find out that actually the equation to consider, in here we don't do the detailed calculation, we just show the result. So the result is show me here that the equation related to the energy band gap, phi 0 barrier height, is also correlate for the DIT, which is interface state density. But why do we have to understand this? Because of this is a very often issue that happen in your own fabricated device, especially if you don't do very good treatment of your service. If you don't do the good treatment of the service, you suffer lots of interface issue. You have very high interface state density. Then you will find out that if your interface for your device are so poor, then your DIT can be achieved approximately with considered for the infinite. Then you will find out that your barrier height here is independent of our metal work function and also electron affinity. So then we lose the chance to modulate our barrier height, because our goal is that we always try to apply the new metal with the new metal work function, try to modulate our barrier height, and try to see that whether we can reduce or increase our barrier height with some new metal or new process. But if your interface state, your interface are so poor, you don't do the good of the treatment of the interface. So then you will face the issue that you have a loss of interface state. That's because it also suggests that you have a poor interface quality. Then you got a very high DIT. So then once you have very high DIT, then you can figure out that now your barrier height is independent of your metal work function and also the electron affinity. So the barrier height now is fixed by the band gap energy and potential phi 0. And then the barrier height is totally independent of the metal work function. And therefore we consider this is a case we call Fermi level become PIM at the surface. And this phenomenon is that's what we call the Fermi level pinning. Then ideal case is that we hope we can achieve the best interface, that we don't have any interface state. Then our barrier height can be very good modulation with our metal work function. So that's the purpose, because then this gives the chance to change the barrier height property with some additional metal, with using a different metal. But if we got the poor interface, we lose this the chance to control our barrier height. And then the Fermi level pinning is actually the big issues in nowadays semiconductor technology. If you try to just put the key term of Fermi level pinning, use a Google Scholar, and then try to search in the last 5 years, I believe you will find like the tons of papers talking about how they face the Fermi level pinning in all kinds of semiconductor, high K, style, 2D, whatever new material. Because as long as the service is poor, we always suffer for Fermi level pinning issue. So this also gives us a motivation why we have to keep improving our interface. For sure, if you are being involved for the process technology, you are trying to fabricate, your seniors, your professor already told you that we should always optimize interface, and because interface is not good, we should try to improve our interface with some surface treatment, with some cleaning process, with some new material, whatever. But the reason is here. Sometimes we just consider this is just way too straightforward, so you might ignore the reason behind. But here is the reason why that the interface should be good enough, because that's always give us a good controllability for the barrier height. And then also this is the last one. Just also we have the several couple slides. So this is Schottky barrier die. So the Schottky barrier die here is the schematic for the Schottky barrier die can be drawn as here. This is a circuit symbol. If you look at in the circuit schematic, so we will see this kind of circuit symbol, which is represent as a Schottky barrier die here, and then this is the positive side and then the negative side of the voltage here. And if you look at the typical IV characteristic for the Schottky junction, Schottky diode is very similar to our PN junction, but the one thing is that this we have this typical Schottky diode characteristic where we have the turn on voltage here. But if we increase our barrier height, then our turn on voltage will increase as well. So we will get this real VT plug. This is because of our barrier height is increased. And we have been talking about lots of it's related to the Schottky junction, but actually, as I mentioned in the beginning, when we talk about metal semiconductor, they should also discussing about the ohmic contact. So the ohmic contact is a barrier that we can achieve the non-rectifying barrier. So the previous Schottky junction is actually achieving the rectifying barrier, but now we are considered a non-rectifying barrier. So in the case of non-rectifying barrier, ohmic contacts are metal semiconductor contact as well. But in the case they are not rectifying contacts, ohmic contact is a low resistance junction. That provide conduction in both directions between the metal and semiconductor. So that means the IV characteristic current voltage for the diode for the ohmic contact, which will be exhibited where the curve will be crossed over the 0 point, and then the slope is represented as a resistance here. So that's a typical case for the ohmic contact characteristic. And then to achieve the non-rectifying barrier, we have to first take into account the metal work function should be smaller than our semiconductor work function. So, for example, in the right-hand side, we have the N-type semiconductor, where our EC, EV, and then we have N-type. And then because of this is N-type, so this suggests our EF is close to our valence band, a conduction band. And now we consider the phi n smaller than phi s. So this is a phi s. And this is our electron affinity. And because of phi n should be smaller than phi s, so therefore our metal work function should be here, where phi n is here. So this is the Fermi energy level in the metal side. So that's a case for the phi n smaller than phi s. But with considering these working functions, these work functions, then we put together, then we can have still the same. Our EF should be the constant through the system. But now, in the right hand side, we have the EC, EV. And because of the lower, smaller work function here, so we start to exhibit this band bending, because this is going to be aligned with this one. So then we can foresee so this is our phi n. And this is our phi m here. So this, based on this band diagram, we can realize that in this interface, actually our Fermi energy is above our conduction band. So this means that this is an extremely high electron concentration, right? Because now our EF is above our conduction band. So this will make the surface more N-type. So this will become the N-type, more N-type. So that's the difference between the Schottky and ohmic. So now we can see that in ohmic, we don't see any barrier. We don't see any built-in barrier, but even this ohmic will try to make our surface become like the heavy N-type, because now our Fermi energy is even upper than our conduction band. So similarly, we can consider the case, if we look at for the case with a p-type semiconductor, then we have to adapt. We have to find the metal has a higher metal work function than the semiconductor work function. And this is a p-type. And then before we connect it, And now we have to find the metal has a larger Wolf function than the phi s. From this Venn diagram, we can start to realize that if we want to make the good ohmic contact on p-type, actually it's not that easy because you want to find the metal. The phi s here is already quite large, but now you have to even find the metal Wolf function has a large Wolf function than the phi s. And then in the world, there are not that so many semiconductor actually exhibit. There are not that so many metal that has this kind of the property, has a large Wolf function than the phi s here. And if we talk about silicon, that's okay. But if you talk about wide bandgap material, and that's getting more difficult. So then, once we put this together, so the mindset to draw the Venn diagram is always the same here. So this is phi p, and this is so with the phi m larger than phi s with this kind of metal Wolf function, so we can make this surface more p-type. Because now our Fermi energy is below our valence band. Okay, so maybe we can finish. I was expecting to finish the chapter, but I think it's a little bit over time. So we'll stop here and we'll continue the rest of the rest of the pages in the next week.